elastomers, and fibers. And then the properties of polymers followed by the application. So this is about polymers, and in the next class we will discuss about ceramics.
Okay, dear students, today we will take up the next part of that, and before we go into that, let's take a quick relook into what we have discussed in the last class. So this was the prerequisite that we discussed yesterday, some information about the second law of thermodynamics is required to understand the analysis of few processes to understand the change in entropy. Second is reversible and irreversible cycles or the processes, followed by what is a Carnot cycle, how we can apply this Carnot cycle to a heat pump, refrigerator or heat engine. TER, that is thermal energy reservoir. So how you define thermal energy reservoir and what are the characteristics of thermal energy reservoir, and then thermodynamic temperature scales. So these are the fundamentals that are required to understand entropy and change in entropy for various processes. So this is the content that we have discussed yesterday. It starts with the inequality of Clausius or Clausius inequality as popularly known as, followed by entropy, a property of the system. So yesterday we have covered up to the Clausius inequality and the significance of Clausius inequality. So today we will take up the second one, that is entropy and how it is a property of a system. Okay. So the remaining are the entropy of a pure substance, entropy change in a reversible process, a thermodynamic property relation, entropy change of a solid or liquid, okay, and then entropy change of a solid or liquid in ideal gas, the reversible polytropic process for an ideal gas, an entropy change of control mass during an irreversible process, entropy generation and principle of increase of entropy. And in the last class we have proved what is Clausius inequality, which is given by the cyclic integral of delta Q by T is less than or is equal to 0. So I just go through quickly how we have covered and what are the equations that we have used to arrive at this required form, that is cyclic integral of delta Q by T using this particular diagram, and what are the conclusions that we have drawn from the previous discussions, that also we have covered. So here of the inequality or the signs what we are using here, less than or is equal to, the equal to sign holds good for internally reversible cycles only, and the less than sign is basically for irreversible ones. So these are the summaries that we have covered in the last class, and we proved one more important factor is that the cyclic integral of any quantity, if it is equal to 0, then that quantity is called the property of a system. So here we have claimed here as entropy is a property of the system, and Clausius observed this and he named this property as entropy, designated symbol S and equated to an internally reversible process, and then the change is obtained as delta S is equal to cyclic integral. And yesterday we took one more important special case as isothermal process. So here an internally reversible isothermal heat transfer process can be given by this equation, and we have taken one example in which we have obtained the change in entropy for this particular case of an isothermal internally reversible heat transfer process as this using simple equation. Next we discussed about the significance of the inequality of Clausius by considering a simple steam power plant and asking the question as whether this inequality of Clausius holds good under certain given change. So these are the equations that I have used. These are the properties that we have determined from the property tables at a different temperature or pressure. So the final answer what we got was this, which is less than 0. Hence, the inequality of Clausius holds good for this given case. Now today, we will take up one more important discussion, that is entropy, a property of the system. So we are moving similar to what we have done in the previous unit of first law, while proving energy as a property of the system. So similarly, we are going ahead here. Okay. So what we are doing here is we are applying the Clausius inequality. What is that Clausius inequality that I am using? Cyclic integral of delta q by t. So this I will keep it as the base. Delta q by t is less than symbol is for irreversible cycles and is equal to symbol is for reversible cycles. Okay. Now the proof is that, let's take up small PV diagram in a similar way how we have calculated for energy. So on this PV diagram, let this be state 1 and this be state 2, which are the random states. Let's not worry about whether this particular process moving from state 1 to state 2 is an expansion process or a compression process. To complete a cycle, let's come back from state 1 to state 2. So here I am moving from state 1 to state 2 via path A, and I am coming back from state 2 to state 1 via path B to execute a cycle. Okay. So this is what is written there. Okay. So let a system or control mass, closed system, undergo a reversible process from state 1 to state 2 along path A, and let the cycle be completed along path B, which is also reversible as shown in the figure, or here also I have drawn the same thing. Let me shade this so that we can apply the equation. So this is the cycle under consideration. Now because this is a reversible cycle, we can write, okay, this equation. So if I consider or assume that this is a reversible cycle, so in the expression what I have to take is the equality sign and not inequality sign. So that is what is mentioned over here. The cyclic integral of delta q by t for this reversible cycle becomes cyclic integral of delta q by t is equal to, okay. So since it is 0, I will proceed with 0. So I am taking the equality sign over here because it is a reversible cycle. Okay. Now this is equal to what? This is equal to, see, the cycle is being executed by two different processes. One via path A from 1 to 2, another is via path B from 2 to 1. So I will be writing here the integrals from 1 to 2 delta q by t. Okay. So I am moving from state 1 to state 2 delta q by t via path A. Since it is cyclic integral, how many such processes are there to execute a cycle? There are now two processes. Now the second process is moving from state 2 to state 1. So it is from 2 to 1 delta q by t by process or via path B. Let's call this as expression 1. Okay. Next is, let's consider another reversible cycle which proceeds first along path C. So now I will be taking a different path. Okay, from state 1 to state 2, let the process begin from path C, which is a reversible process, and then complete along path B. So again it follows the same path, that is path B, to complete a cycle. So this is my new cycle. Okay. So for this cycle also we can write what? Same equation. Again I will be taking cyclic delta q by t is equal to 0 because again here I am considering a reversible cycle, and hence in the expression the equality sign has to be considered. So the first process is from say 1 to 2 1 to 2 delta Q by T, but along path C. So differentiate this with paths. Okay, so this quantity is for path. Now it is coming back from 2 to 1 via B. So it is coming from 2 to 1 via delta Q by T by B. So this is my expression 2. Now if I subtract second equation from the first, that is this equation minus this equation, that will lead to what? So let's write the entire equation and then we'll simplify. So first I'll be writing this as cyclic integral of delta Q by T is equal to 0. Okay, on the left hand side I have 0. This is equal to cyclic integral from 1 to 2 delta Q by T via path A plus 2 to 1 via path B. Now this expression is minus this expression. So left hand sides are equal, so I'm going to equate the two sides. So I'll be eliminating the left hand sides minus this expression. So what is this expression? This expression is equal to integral 1 to 2 delta Q by T C minus of plus, that is minus from 2 to 1 delta Q by T along path B, and this is equal to 0. So I'll be writing that 0 here. Now if you look into this expression, plus delta Q by T through process 2 to 1 via B is written twice. So this cancels out. And now what I have is integral 1 to 2 delta Q by T via process or path A minus integral 1 to 2 delta Q by T via process C is equal to 0. Or this expression can be written as, I transfer one term to the left hand side so that it becomes integral 1 to 2 delta Q by T C. So if I transfer this over here, this becomes C is equal to integral from 1 to 2 delta Q by T A. Okay, so this is the catch. That's what is written over here. So integral 1 to 2 delta Q by T via A is equal to 1 to 2 delta Q by T via C. So what this suggests, what it indicates? It indicates that when the process is taking place from state point 1 to state point 2, whether you go by path C or A and come back by the common path, that is B, doesn't make any difference. That means this particular quantity delta Q by T, which is there in the bracket, okay, is independent of the path, and it depends only on the end states, that is 1 and 2, and hence it is a property of the system. Okay, so this is the conclusion. Since delta Q by T, integral delta Q by T, that is the quantity, is the same for all reversible paths. Similarly, if you select one more path, let's say randomly as D, and if you apply this particular equation, we'll be getting that, okay, delta Q by T for D is equal to delta Q by T for path A. That means it doesn't depend on the path that is selected to complete a process or to execute a cycle. It depends on the states, final states 1 and 2. Hence we conclude that this quantity is independent of the path, and it is already stated in unit 1 what are the characteristics of point function and path function. So based on that, we can say that it is therefore a property of the system. Hence the quantity delta Q by T, which we call it as entropy, is a property of the system, and this property is called entropy and is designated as capital S. And it follows that for a change in substance, okay, a change in property or entropy of a substance in accordance with the relation is given by this expression. So delta S is equal to S2 minus S1, or integral delta Q by T. Okay. So the expression follows the form, or the concluding part is that okay, ds, that is change in entropy, is equal to delta Q by T, okay, between process 1 to 2, and this is strictly for internally reversible process. Okay, but since we have written the change, so this will be, let it be this. So when we integrate it, it becomes S2 minus S1. So whether we are referring to total entropy or specific entropy is purely by the context that what we are using. So obviously delta S, what I have written, or S2 minus S1, what is observed here is, if it is represented in kilojoules, then we are referring to entropy in total, kilojoule per kg Kelvin. Then obviously we are referring to per mass basis, that is specific entropy. So let's proceed to the next one. If I apply it to different substances like pure substance, ideal gas, liquid, solids, how we can evaluate the entropy? So for that, let's understand few important parameters here. Now entropy is an extensive property of a system. Yes, it depends on the mass of a system. Mass changes, the entropy is going to change, just like energy. Next, now values of specific entropy, that is entropy per unit mass, are given in the tables of thermodynamic properties in the same manner as a specific volume and specific entropy. Now we can here include this as one more property to be referred from property tables. So initially we have seen only specific volume, which is expressed in cubic meter per kg, and then enthalpy as expressed in kilojoule per kg. Now we have small s, that is specific entropy, to be referred from the property tables, and its unit is kilojoule per kg Kelvin. So we have added one more property to refer from thermodynamic property tables, okay, along with this. Now unit of specific entropy, as I mentioned clearly, that it is kilojoule per kg Kelvin. This holds good for all pure substances, whether it is steam, that is water vapor, refrigerant, okay, ammonia, whatever. So it remains same. So in general, we use the term entropy to refer to both total entropy and entropy per unit mass. So that depends on the context. In the saturation region, so this is very, very important, the entropy may be calculated using the quality. So again we have the same concept here. Whatever we have referred to the earlier properties in the saturation dome, that is here in this region. So the concept will remain same. Say for example, if I am using on a PV diagram or TV diagram, okay, for a constant pressure line somewhere here, then the value of this particular entropy, yes, depends on the values that I have, SF and SG, and at what level I have the quality. So obviously the value of S at this point is equal to, it is SF for a given temperature or pressure, plus X for the dryness fraction or quality at that point, into either it is SG minus SF, okay, and simplifying that equation we get that X equal to SFG at a given temperature or pressure. Okay. So this is the expression. So whatever we have used to find the specific volume or specific enthalpy in the saturation region, that is mixed state, liquid plus vapor mixture, we are using the same expression here, S is equal to SF plus X SFG. So here SFGs are given in the tables. Most of the times it is given for steam, but for ammonia and all that we have to get this SFG from SG minus SF equation. So let's take some more points related to the pure substance here. Now the thermodynamic properties of a substance are often shown on a temperature entropy diagram. Now temperature entropy means, now I am going to include one more property diagram. What were all the property diagrams that we have studied? One is TV diagram, PV diagram, PT diagram. So these are all called as the property diagrams. Now since we have introduced one more property, which is again an extensive property against an intensive property, we can again draw multiple property diagrams, which is called as the TS diagram. So TS diagram, let me introduce the property diagram. Temperature being intensive property and S being extensive property. So again I am going to use one more diagram called as TS diagram, which is mentioned here, temperature entropy diagram, and on an enthalpy entropy diagram. So this is another diagram called as enthalpy entropy diagram, very informative, but at this point of time we are not using enthalpy entropy diagram, which is popularly called as the Moliere diagram, which we are going to refer from Moliere chart, a person called as Richard Moliere from Germany. Now I have some figures to show you what are the essential elements of a temperature entropy, which is important diagram, property diagram for the analysis. Whereas HS diagram we are not using much here, but definitely we are using this in the ATD subject for refrigerants. So how it looks, a temperature entropy diagram, similar to what we have drawn and understood for the previous properties like PV diagram or be it TV diagram. So now we are going to introduce one more, that is on TS diagram. Okay, so here all the 5 phases of a pure substance can be explained here. If the pure substance is in the compressed liquid region, and how SF is to be calculated. So we have a thumb rule there that the properties are not available for compressed liquid, especially we have limited values. So how to evaluate under such conditions the value of entropy? So again, how the properties are dependent more dominantly on temperature rather than pressure. Here also that value of entropy depends more on temperature rather than pressure when it is in compressed liquid region. So for given pressure or temperature, the S1, say for example, if I draw the saturation dome and if it is in the compressed liquid region, we may not get the range. Okay, so for a given temperature or pressure, what we do is we project it on the saturation dome, the saturated liquid region, and then we drop across and then we find the value of SF, and this is equal to the required point S1, and this is merely dependent on SF at a given temperature and not on pressure. So it is more dominant towards temperature and not on pressure if it is in compressed liquid region. If it is in saturated liquid region, then definitely it is on the saturation dome, and whatever the value that we are going to get for this particular SF at a given temperature or pressure can be taken, just like how other properties are dealt. So I am not going to go in detail as far as the remaining phases are concerned. Then in the mixed region, saturated liquid vapor mixture. So for given temperature, pressure, or both are connected to each other. Okay, temperature and pressure are having a relation. T is a function of P or P is a function of Tsat. But for another property like say quality, an important factor to decide what is the entropy in the mixed region, for which I have already given you the equation. So S is equal to SF plus X SFG. Whereas in the saturated vapor, again it lies on the saturation dome, and directly from the property tables we can get the value of Sg for a given temperature or pressure. Again, when it exists in the form of superheated vapor, then we have either for a given temperature and a combination of pressure, let's say, we can find the value of Sp by going to superheated region. So slowly we'll take up some examples connected to that so that we can explore how to find the value of entropy for when it exists in different phases for a given pure substance. So this is one more, which is called as enthalpy entropy diagram, okay, which is called as HS diagram. Now the general features of such diagrams are same for all pure substances. So the nature of the graph will remain same for all pure substances. So let's take up an example of entropy change of a pure substance and how to evaluate the properties. So I'll read the statement. A rigid tank contains 5 kg of refrigerant 134A, that is R134A, initially at 20 degrees Celsius and 140 kilopascal. The refrigerant is now cooled while being stirred until its pressure drops to 100 kilopascal. Determine the entropy change of the refrigerant during this process. This is what is given. Let's take up the arrangement. The arrangement says that, I'm going to redraw this again. Okay, so let me draw the sketch before we get back to the PPT. So there is a container, closed container is there, which is having R134A as the refrigerant, whose mass is equal to 5 kg. So in this particular arrangement, we have a stirring mechanism. So the moment it rotates, it is going to stir. And because of the stirring, what happens? The internal energy increases and starts radiating heat, and it cools down. This is what the statement is given. Okay, some technical problem was there. Fine. The refrigerant is now cooled while being stirred until its pressure drops to 100 kilopascal. So determine the entropy change of the refrigerant during this particular process. So let me write the states here. Before stirring, what is state 1, and after stirring, what are the states? At state 1, you can say that since it is a closed tank, okay, the volume of the tank is constant and thus specific volume will remain same. So whatever specific volume was there, the same specific volume is here. So I can write it as V1 is equal to V2. Now, at state 1, what is the pressure? Pressure is 140 kilopascal and the temperature 20 degree Celsius, or T1 is 20 degree Celsius. So at these two conditions we can find out what are the entropies, or entropy as well as the specific volume. So from the property table we can refer R134A, page number 49, and 140 kilopascal. Since the values are given in bar, you need to convert the value in bar. So equivalent of 140 kilopascal is 1.4 bar. Now here the values are given for 1.3 bar and 1.44 bar. So what is required is interpolation. Okay. To find the value of entropy, we require interpolation. So the interpolated value for exact pressure of 140 kilopascal is S1, that is obtained value. Okay, S1, that is specific entropy, is 1.0625 kilojoule per kg Kelvin, and its specific volume. Now if you look into the tables, the volume column is given. Before that, density is there. Density for liquid is there, and density of vapor is there. Okay. So how to decide what is the phase of this refrigerant for a given condition? Obviously, for this particular pressure of 140 kilopascal, what is the corresponding saturation temperature? That we have to refer from the property tables. So at 1.4 bar, the saturation temperature is again between -18 and -20, and after interpolation we can say that the saturation temperature Tsat is -19 degrees Celsius. But what is the given temperature? Given temperature is 20 degrees Celsius. Okay. Now since the temperature given is higher, we can say that the phase is superheated. So we have superheated vapor of R134A at initial condition. Clear? Let's find out second state. So in the second state we have only one value known, okay, that is pressure 2, and this pressure reduces to 100 kilopascal. It drops to 100 kilopascal. So I have 100 kilopascal here. So I don't have another property, but the known property from, we can consider this as V2 minus V1, because the tank is closed, and hence we can call this as a constant volume, specific volume problem. So V2 is equal to V1. So what is V1? V1 we have already obtained it again by interpolation and by referring to the value of superheated vapor. So for superheated vapor you have to go to the next page where all the superheated values of R134A for given pressures are given, just like in a normal way how you calculate for other properties. So based on that we can take this as 0.16, okay, 544, again an interpolated value, this much cubic meter per kg. Okay. Now in the state 2, along with the P2, I have V2, okay, which is equal to V1. But I don't know the phase. So first I have to decide what is the phase after the heat is being transferred, okay, from the tank after stirring. What is the phase? So to identify at this condition what is the phase, first you need to find out the corresponding specific volumes of the saturated liquid and specific volume saturated vapor for a given pressure of 100 kilopascal. So again from property tables, at exactly 1 bar, 100 kilopascal means 1 bar, whereas the corresponding temperature is minus 26 degrees Celsius, fine. The value of Vf, okay. Now since it is not given directly as the specific volume, density is given, but we know how the two are related, okay. Now density is equal to the reciprocal of the specific volume or vice versa, or specific volume of a liquid is equal to the reciprocal of its density, okay. So now the density is 1374, okay, it is 1374 kg per cubic meter. So 1 upon 1374 will give you exactly or nearly equal to 0.7777258, 0.7777258 cubic meter per kg. This is how we can get the value of Vf. Now this particular value is required to understand the phase. Similarly Vg is directly given from the table. So for 1 bar the corresponding value is 0.19255. So here it is 0.19255 cubic meter per kg. This is what I have mentioned there. Now if you look into the given value of V2, which is equal to V1, and Vf and Vg, given value lies in between this. So if I draw a corresponding PV diagram, the value Vf is here, the value of Vg is here, and the given value V1 is equal to V2 lies in between, and hence we have, okay, a refrigerant is saturated liquid vapor mixture at the final state, since the value of V2 lies between Vf and Vg. So here somewhere the value of V1 is somewhere. So this says that phase of the refrigerant at state 2 is mixed, liquid plus vapor, liquid plus vapor. So when it exists in the form of liquid plus vapor mixture, first and foremost thing is we need to find out the quality, the value of X. So let's find out the value of X. The value of X can be obtained as X is equal to the given equation, simple, okay, or if you want it, you can calculate it for V2 is equal to, it is Vf plus X Vfg, or if Vfg is not there, then we can calculate it by Vg minus Vf, and therefore X is equal to, it is V2 minus Vf divided by, it is Vg minus Vf. All the values are to be obtained at state 2, because we require after stirring, when the heat is transferred, what is the value of S2, and hence I want V2, that is at state 2. So at state 2 we have a pressure of 100 kilopascal. All these values are to be calculated for 100 kilopascal, that is 1 bar. So again from the R134A property tables, we can get the value of Vf and Vg, which is already there, and if I substitute in the equation, I'll be getting the value of X, or to make it very clear, we can get this as X2, state 2, is equal to, okay, how much? 0.859. So it is 0.859, or it is 85.9% dry and remaining is wet. Okay. So now I can use the expression entropy in the mixed region to find the value of final entropy. So that is S2 is equal to SF plus X2, whatever we have used, SFG. So all these are to be obtained at 100 kilopascal from the property tables of R134A. So again, SF the same way is to be obtained from the property tables. So here it is given entropy in kilojoule, liquid SF and vapor SG. So for 100 kilopascal, the value of SF is, okay, it's given as 0.07182 and X value is 0.85, and SFG. In some cases, SFG is not provided in the table, just like in the present case. So how we have to calculate this SFG? So this SFG has to be calculated by converting that into, it is SF plus X2, it is SG minus SF. So all are to be calculated for 100 kilopascal. So now you can substitute separately for what is SG, which is given for say 1 bar as 0.08802 after the differences. So substituting all the values, getting the value of S2, which is equal to 0.8278 kilojoule per kg Kelvin. Now once you know S2, what is asked? Determine entropy change. So this is not the end of the solution. We still need to calculate what is entropy change. So S1 we know before the process is to take place, that is stirring process, and for a pure substance in a tank. So finally what I'll be using is this equation. Okay, what is that? Delta S, entropy change in the tank for a given mass of 5 kg is equal to m S2 minus S1. So this particular equation can be developed like this. We know that it is S2 minus S1, okay, but these are all extensive property converted into intensive. So it comes with the mass m. So this becomes S2, capital S2 minus capital S1, which is nothing but delta S. So this is how we can calculate the change in entropy. So given mass is 5 kg, S2 you have calculated it to be 0.8278 minus S1 from the state 1 can calculate it to be 1.062 kg, and the final answer after substitution is minus 1.173 kilojoule per Kelvin, not per kg. Remember here we are calculating it for total entropy. Okay, so this is how we can convert the values. Entropy change of a pure substance in a tank. Now this is the final property diagram, that is a TS diagram. So let's understand how to draw this TS diagram. A saturation dome as usual. Now as per state 1, okay, which is in the superheated region, so randomly mark, you can randomly mark state point 1 in the superheated region. Now the question comes, how to connect the 2 points, whereas state 2 is in the mixed state. Okay, so randomly mark second point also, which is state 2. Now you have to join this. So either you can go by say this and this and get the process done. So this is going to give you the entropy change. So this is S2 and this is S1. So delta S is equal to, it is final state minus initial state. So it is decreasing from here. S1 we are moving towards the left hand side. So the value of entropy change is decreasing, negative. Delta S is minus. Now the same thing you can, or we can draw it on a PV diagram or on TV diagram. Now since the pressures from 140 kilopascal to 100 kilopascal is decreasing, temperature from 20 to minus 26. Minus 26 means for 100 kilopascal, what is the saturation temperature? So that is minus 26. Both the values are changing. So it becomes essential to note the change here, that on PV diagram or on TV diagram, the change is that on PV diagram we have a downward trend of temperatures, and on TV diagram we have upward trend of pressures. So these are all constant temperature lines, and these are all constant pressure lines. So how to mark it on these two diagrams? If you refer that previously we have started with a condition that volume of the tank is constant, and thus it is V2 equal to V1. This is important, and that's the reason why both TV and PV diagrams are not that informative, and hence we are shifting to TS diagram to know the property or the phase change. So here if at all I have to mark, this T is having higher temperature here, okay. So this is going to give you a total straight line like this. So this is state 1 and this is state 2, and if I extend it, it's going to be V1 is equal to V2 on volume line. Similarly over here on the pressure line, okay, it is initially in the final state and then enters into V1 is equal to V2. So it is not that informative on TV or PV diagram, it's just a straight line, and hence we are shifting on to the TS diagram so that we can analyze the change in the property values. Okay, we'll stop here. The next class will start with the entropy change in a reversible process.